Hi, I'm Miss Curious. I have a small quiz for you today. Observe with me my friends, Tina and James, who are involved in some activities. What do you think is common in all these scenarios? In all these scenarios, force is being applied to move or stop a body. However, the force applied is of different types. In this lesson, you will learn about the effects of force and the types of force. At the end of this lesson, you will be able to define force, identify the effect of force on an object, identify the direction of net force in a given situation, and identify the type of force applied in a given situation. Let's analyze the situations we observed earlier. Can you make out exactly what Tina and James are doing in each situation? In the first situation, James is pulling a wooden log.
Oof, this is heavy.
In the second situation, James is hitting or pushing a ball.
Okay, what a load of stuff. Now for billing.
In the third situation, Tina is pushing a shop cart towards the billing counter.
Move out of my way.
Don't push me, you move.
Finally, in the fourth situation, Tina and James are both pushing each other with equal force. That's why neither of them is moving. So, what's the conclusion? Did you notice that James and Tina are either pushing or pulling when they apply force? Therefore, we can say that force is the push or pull that occurs due to the interaction of two bodies. Force is generally denoted by the capital letter F. Now let's look at the other aspect of force, its impact. What are the effects of force applied on objects? A force can change the state of rest or of motion of the object on which it is applied. The state of motion of an object is described by its speed and the direction of its motion. If the speed of an object is 0, it is said to be at rest, else it is in motion. To understand better, let's observe a car race with James.
The race has started. Look at all those cars shooting off.
The cars that were at rest are now driving at a high speed. In other words, their state of motion has changed. However, the audience is still at rest. A change in speed always results in the change in state of motion. To understand how force changes the state of motion of a body, let's check out some of the scenarios from our everyday lives. Here, Tina is in the park walking the dog.
Terry, slow down.
She is trying to stop the dog from running away. On the other hand, look at James pushing the shopping cart, which is initially at rest. Both Tina and James are applying force. What is the effect of force on Tina's dog and on James's shopping cart? You observed that the dog was moving, and it stopped when Tina applied force on its leash, whereas the shopping cart was stationary before James pushed it. Now let's observe what happens when James plays hockey.
James, faster, towards the goal.
The ball ahead of him is moving with slow speed. When James hits the ball again in the same direction, it moves with more speed. While playing hockey, James flicks the ball passed to him towards the goal by applying force through his hockey stick. In doing so, he changes the direction in which the ball was moving, you can say a force can change the direction of motion of the object on which it is applied. Now, let's look at what James and Tina are up to.
Hey, those are some interesting shapes.
Yeah, let's see how he does it.
Look at how the balloon vendor is blowing the balloons and then squeezing them to make funny shapes. He changes the shape of the balloon by applying force at different points on the balloon. Tina does something similar when she uses plasticine to make cartoon characters in her modeling class. She models the clay by pressing it with her fingers at various points. So, as you can see, force can change the shape of the object on which it is applied. That is, what happens when you crumble a piece of paper? The shape of the paper changes, right? To summarize, a force may change the state of motion of an object, change the direction of motion of an object, or change the shape of an object. We spoke about the push and pull types of force as well as the effects of force. How about the magnitude of a force? Are all forces equal? Let's observe Tina and James in a competition.
I bet I can kick this ball farther than you can.
Really? Let me see.
Looks like James won. He could kick the ball further because he applied more force. The force applied by Tina and James differed in quantity or magnitude, even though it was a push force in both cases, and resulted in the movement of the ball across the field. To sum up, the quantity of force is known as its magnitude, which is the measure of the force. A larger force has more magnitude and vice versa. So far, you have seen effects of single forces in terms of pulling and pushing. But in real life, there are often multiple forces acting on a body simultaneously. In such cases, we must consider the result of the multiple forces acting on the body. This resultant force is called the net force. Sounds confusing? Let's look at some examples. Tina is applying force to push the table to the wall, but she is unable to do so. The table seems to be too heavy for her to push forward alone.
Hey James, come, lend me a hand please.
Observe what happens now. When James and Tina both pushed the table together, it was easier for them to move the table. This shows net force is bigger than the individual forces, in this case, where the individual forces act in the same direction. Conversely, the net force can reduce when two forces act in opposite directions. Do you remember the story of the two goats crossing a narrow bridge in opposite directions? Neither of them wanted to go back and give way to the other. They pushed at each other and were initially stuck in one spot. However, the bigger goat kept pushing with increasing force till the other goat gave way. Here, the net force was zero initially, as both the goats were pushing in opposite directions with equal force. When the bigger goat increased the force applied, it succeeded in moving ahead. The net force in this case acted in the direction of the individual force that was of higher magnitude. Observing these scenarios, we can conclude that in the case of multiple forces applied on an object, if the two forces act in the same direction on an object, the net force acting on it is the sum of both the forces. Conversely, if the two forces act in the opposite direction on an object, the net force acting on it is the difference between the two forces. Therefore, net force is the sum of all the forces acting on the body. The magnitude and direction of the net force on the body depends on the magnitudes of the individual forces and their directions. Hey Tina! Hi James!
Hi, Miss Curious. What mysteries are you solving today?
Well, I'm exploring concepts related to force. And I have a couple of questions for you. Tina, can you lift your shopping bag without holding it? James, can you pull open a desk drawer without touching it?
Of course not. That's a silly question.
Right.
I agree. So, generally, objects have to be in contact for the application of force.
Absolutely.
But I can think of a situation where force is applied even though you cannot see the contact between objects. Can you guess where this is possible?
It's a magnet you're talking about.
You got it. A magnet can attract a nail towards itself without even touching it, right? Hence, we can classify forces as contact forces or non-contact forces. A contact force is a force between two objects that are in contact with each other. Any force that is exerted without any contact between two bodies is a non-contact force. There are two very common examples of contact forces that you observe often. They are muscular force and frictional force.
I understand muscular force. I have well-developed muscles.
That's right. Muscular force is any force exerted by a person using muscles. Muscular force enables us to perform all activities involving the movement or bending of our body. Muscular force is involved in all your actions. For example, when you throw a ball, ride a bicycle, or lift weights. But it's not limited to human beings. You see animals walking, galloping, or eating. All these actions also involve muscular force. Animals like bullocks, horses, and donkeys are used to draw carts and perform other tasks for us. All these animals use muscular force to perform such tasks.
So, what about the other contact force? Frictional force?
Frictional force is the force that opposes motion. That is, it acts in a direction opposite to that of motion.
Where can we see friction in action?
Consider a ball rolling in the field. You'll notice that it comes to rest in few moments. Now, look at this car when the engine has been switched off. Its speed decreases gradually. Finally, it stops. Do you observe anybody exerting force to stop the car or the ball?
Nobody.
Even then, something seemed to stop the movement of both these objects, right? Friction is responsible for changing the state of motion of objects in both these situations.
But what about non-contact forces? Are there any other non-contact forces apart from magnetic force?
As a matter of fact, there are. Non-contact forces can be magnetic force, electrostatic force, or gravitational force. Let's consider them one by one. The force exerted by a magnet on a certain metallic object or another magnet is known as magnetic force.
Dad gave me a magnet the other day. he was showing me his toolkit, and I discovered that the magnet was attracting all the nails in the box.
Yes, magnetic force can do that. Let's show Tina as well. Take a few shoe nails and place them in one end of a wooden table. Bring a magnet and place it on the farther end of the table. You see no change in the position or state of motion of the nails. Now, bring the magnet closer to the nails, gradually dragging it over the table. As the magnet comes near enough to the nails, you observe that the nails start shifting position and trying to get closer to the magnet. Bring the magnet even closer to the nails. The nails eventually get attached to the magnet.
But magnets can repel also, right?
Yes. You may have learned in your class that the like poles of a magnet repel each other. If you place two magnets with their like poles facing each other and try to bring them closer, you will find that the magnets are resisting the movement. They are pushing each other away. So, can you see how magnets exert pull as well as push force on each other?
You're right. The magnet pulls nails to it, but it pushes away the like pole of another magnet, and all without actual contact with the nails or the other magnet.
Very good.
So, what about electrostatic force? Is that related to electricity?
Good guess. Electrostatic force is the force exerted by a charged body on another charged or uncharged body. Have you ever noticed how your comb crackles when you pull it through your hair?
Yes, quite often.
If you bring such a freshly used comb near bits of paper, you'll observe that the paper bits come and attach themselves to the comb. This is due to electrostatic force. The comb gets charged while you are combing your hair. Now, let's see Tina drop a ball from the balcony.
Now I'll have to go down to get it.
But why do you think it went down? Why didn't it float around in the air?
How can it? Everything comes down to earth, whatever height you drop it from.
You're right. But there is a reason for that. The earth exerts a force of attraction on all bodies on and near its surface. This force of attraction exerted by the earth on any other body is called gravity. In fact, like earth, all bodies in the universe attract each other. The force with which all bodies in the universe attract each other is called gravitational force.
Oh, Dad was saying something about Newton and gravity the other day.
Newton started thinking about gravitational force when an apple fell from a tree on his head one day. He started wondering why the apple didn't stay up. This brings you to the end of this lesson on force. Now, you should be able to define force, identify the effect of force on an object, identify the direction of net force in a given situation, and identify the type of force applied in a given situation. Let us take a look at a billiard table, something most of us are all familiar with. The balls are all stationary. What will make them move? A push from the stick, that is, an external force. The important thing to note here is that without this push, or an external force, the balls will remain at rest for an infinite duration. Thus, motion is a direct result of force. This relationship between force and motion was studied by Galileo and Newton. Galileo was the first to abstract from what he and everyone else saw. An object in a state of motion possesses an inertia, that causes it to remain in that state of motion unless an external force acts on it. Sir Isaac Newton further studied Galileo's ideas on force and motion and presented three fundamental laws that govern the motion of objects. These three laws are known as Newton's laws of motion. In this lesson, you will learn about Newton's first law of motion and inertia. At the end of this lesson, you will be able to explain Newton's first law of motion, explain the concept of inertia, examine inertia based on object size. Newton's first law of motion states that an object will remain at rest or continue to move at a constant speed in a specified direction unless an external force acts upon it. This law relates force applied on a body to the change in its velocity. There are two aspects of this law that we need to consider. First, an object at rest will remain at rest unless an external force is applied to it. All objects at rest conform to this. For example, on a golf course, a ball on a tee remains at rest until the golfer hits it. When the ball is hit, a force is applied setting the ball in motion. The second aspect relates to a moving object. An object in motion will move at a constant speed and in a fixed direction unless an external force is applied on it. Consider an artificial satellite revolving around the Earth. It moves with a constant speed and in a fixed orbit. The orbit of satellite will not change on its own. In case the satellite is required to change its orbit, booster rockets are fired up to exert force on the satellite. This changes the speed and direction of the satellite. You may have questions about the validity of this law. This is not how things really work around you, is it? For example, if a batsman strikes a ball, the ball eventually comes to a stop, no matter how forcefully the batsman hits it. This has been explained through the concept of friction. Friction is a hidden force that arises between two surfaces in contact. This force acts in a direction opposite to the direction of the force trying to move an object. Friction is used in our daily lives to slow down and stop moving objects. To put it simply, the essence of the first law of motion is that all objects resist a change in their state of rest or of uniform motion. For example, when you try pushing a boulder at rest, it resists motion initially. However, if you exert enough force, the boulder starts rolling. Consider another situation where a truck is carrying an unfastened load. When brakes are applied suddenly, the truck stops but the load moves forward and hits the back of the cabin. This is because the load tries to retain its state of motion. This tendency of undistributed objects to stay at rest or to keep moving at a constant velocity is called inertia. You can see this concept when you play a game of caroms. If a fast-moving striker hits a vertical stack of coins, sometimes only the bottommost coin in the stack is pushed out. The rest of the coins in the stack remain intact. The stack of the remaining coins comes down vertically, retaining their position of rest. This is because no force was applied directly on them. Now let's look at an object that retains its state of motion. A satellite orbiting the Earth continues to revolve with constant velocity, as no external force such as friction is applied on it. In real life, on Earth, it is difficult to find an ideal frictionless surface. Let's analyze some more cases where we observe this law at work in our everyday life. Look at the standing passenger in this bus. The bus starts suddenly and the passenger is pushed back. This happens because the lower part of the passenger's body, which is in contact with the bus, begins to move with the bus. However, the upper part of the body tends to maintain its state of rest. As a result, the upper body tends to fall backwards and the passenger experiences a jerk. Similarly, when the bus slows down by applying a sudden brake, a standing passenger tends to fall forward. This is because, at this time, the lower part of the body, which is in contact with the bus, tends to stop while the upper part of the body resists the change and tries to maintain its state of motion. Now that we know what inertia is, the next question is inertia equal for all objects? There isn't a yes or no answer to this question. Inertia is proportional to the mass of an object. This is evident when you try to push empty boxes versus boxes filled with packages. It is easier for you to push an empty box, right? Kicking a football around is fun. But would you try kicking large stones of the same size? No, that would hurt, as you can see. So, remember, the larger the mass of an object, the greater is the inertia. Based on this, if you compare a car and a train, and a plastic coin and a nickel coin, which of these would have more inertia? You would need to compare the mass of each set of objects. The mass of a train is more than the car, so the train will have more inertia. Similarly, the mass of a nickel coin is more than that of a plastic coin. Hence, the nickel coin will have more inertia. We are all advised to wear seatbelts while driving. Why do you think it's so important? Let's find out. When the driver of a car applies brakes and the car slows down or comes to a halt, have you noticed that the driver's body tends to continue in the same motion due to inertia? Inertia is the reason the driver is pushed forward in such situations. The seat belt restrains the body and prevents this forward motion. By doing so, it protects the driver from injuries that may result on sudden braking at high speeds. In absence of seat belts, applying sudden brakes may cause the driver to hit the steering wheel or front panels of the car violently, resulting in an injury. As the first law of motion explains the concept of inertia, it is also known as the law of inertia. This brings us to the end of the lesson on the first law of motion. In this lesson, you have learned about Newton's first law of motion, inertia, and the link between mass and inertia. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. Why does the ball come back to you every time you kick it towards the wall? Looks like the wall is kicking it back to you, doesn't it? The speed of the return of the ball also differs based on the force of the kick aimed at the ball. Actually, the wall exerts a force on the ball to return it to you. This force is a reactive force and is induced by your action, that is, kicking the ball to the wall. What happens when you try pushing a wall? It pushes you back in reaction. Newton's third law relates the reactive force to the force applied on a body. In this lesson, you will learn about the third law of motion and conservation of momentum. At the end of this lesson, you will be able to state Newton's third law of motion, explain the law of conservation of linear momentum, and identify the situations where this law is observed in daily life. Newton's third law of motion also known as the Law of Reactive Forces, states, when one object exerts a force on another object, the second object instantaneously exerts a force back on the first. These two forces are always equal in magnitude but opposite in direction. These forces act on different objects but never on the same object. According to this law, if we push an object, it pushes us back. And if we pull it, it pulls back with a force of equal magnitude. Let's revisit the situations we observed at the beginning of this lesson. The boy kicks the ball to the wall, say with a force of 10 Newton. The wall kicks the ball back with equal force. The direction of the force exerted by the wall is opposite to the direction of the boy's kick. One force acts on the wall, while the other force acts on the ball. In the second situation, the man pushes the wall with a force, say 100 Newton. What happens to the wall? The wall also pushes back with a force of equal magnitude. Both these forces act in directions opposite to each other. And one force acts on the wall while the other acts on the man. Let's verify this law using two spring balances, A and B. Spring balance A is fixed to a wall with the other end hooked to spring balance B, as shown. When a force is applied on spring balance B, it also stretches spring balance A. Observe the readings on both A and B. Both springs show equal expansion, indicating equal magnitude of force on the springs. The direction of expansion of spring in A is opposite to that in B. And as you pull B, its spring expands due to the applied force. Since A and B are hooked to each other, B exerts force on A, expanding the spring therein. You can say A is reacting to the pull force on B. Here, the force due to B is exerted on A, while the force due to A is exerted on B. To put it simply, the essence of the third law of motion is that every action has an equal and opposite reaction. Here, action and reaction refer to the applied force and the reactive force. This means action and reaction always occur in pairs. For instance, consider a boxer punching the sandbag. The sandbag seems to be punching the boxer back. Thus, force exerted by the boxer and the force with which the sandbag hits back form a pair. Let's examine some other situations where this law can be observed. If you push a spring fixed to a metal block with a force F, the spring pushes against your hand with same magnitude of force, that is, F. Let's now examine how this law applies in the case of a collision. Suppose two trucks, one big and another small, are involved in a front-rear collision. One would think only the small truck would suffer damage. However, that's not quite true. As you can see, the bigger truck also suffers damage. This is because when the bigger truck hits the small truck also hits back with a force of the same magnitude. Hence, there is damage to the bigger truck. The functioning of a lot of applications we use is based on Newton's third law of motion. Let's look at a few examples. Blow a balloon and release it without tying up the opening. The air inside the balloon escapes downward through its opening. The escaping air exerts pressure on the balloon, providing a thrust to the balloon and pushing it in the direction opposite to the direction of the escaping air. Here, the escaping of air can be regarded as the action. The motion of the balloon in the opposite direction is the reaction. Thus, the reactive force of the escaping air keeps the balloon afloat in the air till the air in the balloon is exhausted. Jet engines also work on a similar principle. A jet engine pushes air backwards during flight. As a reaction, the aircraft is pushed forward. If you like swimming and diving, you must be familiar with diving board. During a swimming event, a gymnast hops on the free end of the diving board before jumping off. The hopping action pushes the board down. When the board is released, it pushes the gymnast up in reaction. The reactive force enables the gymnast to jump higher. This shows that every action force is matched with the reaction force, which is equal in magnitude and opposite in direction. In the third law of motion, you see two equal forces acting simultaneously against each other on two objects when an event such as collision occurs. However, according to the second law of motion, the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction of the applied force. This means that during a collision, the rate of change of momentum of one object is related to that of the other, since the force exerted by both the objects is equal. However, the sum of the momentum of both the objects before and after the collision remains constant. Hence, in the absence of any external force, the total momentum of the system is conserved. This is known as the law of conservation of momentum. In this lesson, we will focus on linear momentum. Therefore, the law of conservation of momentum in this lesson actually refers to conservation of linear momentum. To understand this law, consider two spheres, A and B, of mass ma and mb, moving along a straight line. A is following B, and both these objects display unequal initial uniform velocities. Let these velocities be UA and UB respectively. The magnitude of velocity of A is greater than that of B. Momentum of an object is the product of its mass and velocity. Therefore, the momentum of each sphere is mass times its velocity. Assuming there are no external forces, the total momentum in the system will be equal to the sum of the momentum of both the spheres. Since the spheres are moving to unequal velocities along the same path, they will collide at some point. Let's assume that after collision, both the spheres A and B move with uniform velocities VA and VB respectively, in the same direction as that before collision. As the spheres move along a straight line before and after collision, their momentum is said to be linear momentum. We can use the second law of motion to find the relationship between the momentum of the spheres before and after the collision. According to the second law of motion, force is proportional to the rate of change of momentum. Upon collision, the force exerted by A on B, FAB, is equal to MB multiplied by VB minus UB divided by T. Similarly, the force exerted by B on A, FBA, is equal to MA multiplied by VA minus UA divided by T. According to Newton's third law of motion, these two forces are equal in magnitude and opposite in direction to each other. Here, FBA is the force of action while FAB is the reactive force or reaction. Since it is a reactive force, it is always indicated with a negative sign. By equating both these forces and simplifying the equation, the sum of the initial momentum of both the spheres before collision is equal to the sum of their final momentum after the collision. Hence, we can conclude that the total momentum in the system is conserved. You can observe the phenomenon of the conservation of linear momentum in a variety of everyday activities. For example, look at Jim getting off the boat. While jumping out of the boat onto the pier, Jim loses balance and falls into the water, as if someone pulled the boat back from under his feet. This is because when Jim exerts force to jump out of the boat onto the pier, he pushes the boat backward in reaction. Thus, you can see Newton's third law of motion at work. When Jim is in the boat, the total initial momentum of his body and the boat is zero. In jumping out of the boat, he exits that system using some momentum. Equal momentum is conveyed to the boat, pushing it back. This is how Jim falls into water. Similarly, consider the example of a cannon. When a cannon is fired, the cannonball shoots off with a very high velocity. Since the force exerted by the cannon on the cannonball is equal to the force exerted by the cannonball on the cannon is pushed back in recoil. If the vanes of the cannon are not locked, the momentum due to recoil makes the cannon roll backwards. The law of conservation of momentum, formulated nearly 3 centuries ago, is an inference from a large number of observations and experiments. It is interesting to note that not a single situation observed so far contradicts this law. This brings us to the end of this lesson on the third law of motion. In this lesson, you have learned about Newton's third law of motion and the law of conservation of momentum. Let's quickly summarize the 3 laws of motion. The first law states that an object will remain at rest or continue to move at a constant speed in the same direction unless an external force acts upon it to change the state. Newton's first law of motion gives the concept of force. The second law states that the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction as that of the applied force. Newton's second law of motion gives the measurement of force. The third law states that every action has an equal and opposite reaction. Newton's third law of motion gives the application of force. The section Unsolved Problems provides you an opportunity to review a model problem based on the third law of motion. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. Oops! Now, is that ball coming back or not? Looks funny, doesn't it? But that's the way things could be if there was no gravitational force to hold things to the Earth's surface. In this lesson, you will learn about the universal law of gravitation, gravitational force, and its effect on a freely falling body. At the end of this lesson, you will be able to explain gravitation, state the universal law of gravitation and explain its significance, derive the expression for gravitational force between the Earth and an object on the Earth's surface, calculate the acceleration due to the gravity on Earth, differentiate between mass and weight, and compare the weight of an object on the Moon with its weight on Earth. When an apple fell on Newton's head, he figured out that the Earth exerts a force of attraction on all bodies near its surface. The force of attraction exerted by the Earth on any other body is called gravity. Gravity is what brings things down again when we throw them up. Like Earth, all bodies in the universe attract each other. The force with which all bodies in the universe attract each other is called gravitational force. The revolution of the moon around the Earth is also a result of gravitational force, which acts towards the center of the Earth. Such a force exerted on a body moving in a circular path that acts towards the center of the circular path is known as centripetal force. Newton originally thought that like an apple or a ball, all objects should fall to Earth. However, based on his study of centripetal forces, he was able to explain why this does not happen. When a body A is in circular motion around another body B, it experiences a force directed away from the center of the circular path, which is equal in magnitude and opposite in direction to the centripetal force. This prevents the two bodies from moving towards each other due to gravitational force of attraction between them. This is the reason that the moon and the planets revolve in their respective orbits instead of falling on each other. For a better understanding of centripetal force, let's observe a game of hammer throw, an Olympic athletic event. Each thrower swings a hammer around and releases it at a point such that the hammer flies off in one direction. You can observe that the hammer gradually gains velocity as the thrower swings it around, and the hammer flies off in a straight line which is tangent to the circular path of its revolution. While the athlete is swinging the hammer, that is, the hammer is in revolution, its direction of motion and hence its velocity changes continuously. This change in velocity produces acceleration on the hammer. This acceleration is directed towards the center of its circular path. Acceleration directed towards the center results in a force directed towards the center. This force is called the centripetal force, which means a center-seeking force. The reason for the motion of the moon around the Earth is similar to that of the motion of the hammer just discussed. The gravitational force of attraction between the Earth and the moon provides a centripetal force for the moon. In the absence of centripetal force, the moon would follow a tangential path similar to that observed in the case of the hammer discussed. In that case, our moon would have flown away from the Earth long back. Consider the force that holds things to Earth, the occurrence of tides due to the motion of the moon and the sun, the revolution of the moon around the Earth, and the motion of planets around the sun. What do you think is common among all these phenomena? Nothing, you may say. However, through the universal law of gravitation, Newton explained the relationship between several such phenomena that were earlier thought to be unrelated. Newton's universal law of gravitation states that every object in the universe attracts every other object with a gravitational force, which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The gravitational force acts along the line joining the centers of the two bodies. The law is universal since it is applicable to all objects, regardless of their masses or their positions in the universe. To derive the expression for the universal law of gravitation, consider two spherical bodies. Let m1 be the mass of the first body m2 be the mass of the second body. R be the distance between the centers of the two bodies, which is generally referred to as the distance between the bodies. F be the force of attraction between the two bodies. According to Newton's universal law of gravitation, gravitational force between two bodies, F, is directly proportional to the product of masses of both the bodies, m1 and m2, and inversely proportional to the square of the distance between them, r. By combining both these relationships, we get the gravitational force between the bodies as F proportional to m1 m2 divided by r square. To equate this relationship, we use a constant of proportionality, G, which is the universal gravitational constant. This gives us F is equal to G m1 m2 divided by r square. If m1 and m2 each equals 1 kilogram and r equals 1 meter, you get F is equal to G. Thus, the universal gravitational constant is numerically equal to the gravitational force between two bodies, each possessing a unit mass, separated by a unit distance. The SI unit of the universal gravitational constant is Newton meter square per kilogram square. Henry Cavendish found the value of G with the help of a sensitive balance. G equals 6.67 into 10 raised to the power minus 11 Newton meter square per kilogram square. In deriving the expression for the gravitational force of attraction between two bodies, Newton used Kepler's third law of planetary motion. This helped him conclude the second part of the relationship known as Newton's inverse square rule. This rule states that the gravitational force F between two bodies is inversely proportional to the square of the distance between them. In deriving the inverse square law, Newton assumed that the planetary orbits are circular. If a planet revolves around the Sun in a circular orbit of radius r with a velocity v, also referred to as the orbital velocity of the planet, then the force on the planet is F proportional to v squared divided by r. Let's call this equation 1. The orbital velocity of the planet, v, is equal to 2 pi r divided by t, where t is the orbital period of the planet. Squaring both the sides and simplifying, we get equation 2. V square is equal to 4 pi square r cubed divided by rt square. Substituting equation 2 in equation 1 and simplifying, we get equation 3. In equation 3, 4 pi square is a constant. According to Kepler's third law, r cubed divided by t square is also constant. Therefore, we can eliminate these constants from the relationship. Eliminating the constants, we get the relationship as F proportional to 1 divided by r square. Newton extrapolated these findings to all the bodies in the universe. Therefore, the gravitational force F is inversely proportional to the square of the distance between the two bodies. As we mentioned before, when you throw an object up, it comes down due to gravity. Thus, when an object such as this boulder is pushed or thrown from a height, it falls to the earth. Such an object is said to be in free fall. An object is in free fall when it falls to the earth under the sole influence of gravity. A fruit falling off a tree or a sandbag thrown off a hot air balloon hurtle towards the earth in a free fall. However, a parachutist descending from an aircraft is not in free fall, since he uses the parachute to counter the gravitational force of Earth. A freely falling body is always under the influence of the gravitational field of the Earth. But not all the bodies under the influence of the gravitational field of the Earth are freely falling bodies. A body under the influence of Earth's gravitational field can be a body dropped from a certain height, like a ripe fruit falling off a tree. A body projected vertically downward from a certain height with some velocity, such as a ball thrown down by a boy from the 5th floor of a building. Or a body projected vertically upward, for example, a stone thrown vertically upwards. Objects in free fall move only in one direction. However, their velocity changes as they fall. A change in velocity results in acceleration. The acceleration of a freely falling body due to the gravitational force of the Earth is known as acceleration due to gravity. Acceleration due to gravity is denoted by the small letter g and is measured in meter per second square. How can you determine how long it will take an object in free fall to reach the Earth from a specific height? To perform such calculations, you need to know the value of acceleration due to gravity. So, let us now derive the expression for acceleration due to gravity g. Consider a freely falling object of mass m. Let the capital letter M denote the mass of Earth. D be the distance between the free falling object and the center of the Earth. And R be the radius of Earth. Since the object is in free fall, the gravitational force F on the object is the product of its mass m and acceleration due to gravity g. Let's call this equation 1. The gravitational force F between the Earth and the free-falling body can also be calculated using Newton's universal law of gravitation. F is equal to g into m divided by d square. When the object is near to or on the surface of the Earth, the distance d is taken as equal to the radius of the Earth r. Let this be equation 2. By equating 1 and 2, we can calculate the acceleration due to gravity as g is equal to g multiplied by m divided by r square. Since the Earth is not a perfect sphere, its radius is maximum at the equator and minimum at the poles. Hence, the acceleration due to gravity is greater at the poles than at the equator. However, this difference is negligible for bodies on Earth. To calculate the value of acceleration due to gravity g, we need to substitute the values of universal gravitational constant g, mass of the Earth m, and radius of the Earth r in the expression we derived. On substituting and simplifying, we find that the value of g is approximately 9.8 meter per second square. Acceleration due to gravity at a place on Earth is the same for all bodies, irrespective of their masses. Let's use two identical objects with different masses to verify this statement. Drop a metallic ball and an identical wooden ball from a height. Do you notice that both reach the surface of the Earth simultaneously? Since the mass of the metallic ball is greater than that of the wooden ball, the force of gravity on the metallic ball is greater than that on the wooden ball. However, it doesn't seem to make the metallic ball fall faster than the wooden ball. This proves that acceleration due to gravity on Earth is the same for all bodies irrespective of their masses. In your study of motion, you have learned about the equations of motion. There are three equations of motion. 1. V is equal to U plus AT. 2. S is equal to UT plus half AT square. And 3. V square is equal to U square plus 2AS. These equations relate displacement, velocity, and the acceleration of a body. The acceleration of all freely falling bodies is due to gravity. Therefore, we can simplify these equations for freely falling bodies. Now let us observe how these equations of motion are modified for freely falling bodies in all three cases. The first one is the case where a body drops from a certain height. Here, the initial velocity of the body u is 0. The acceleration of the body a is the acceleration due to gravity g. This value is positive because the velocity of the body increases as the body descends. Let's consider how the three equations change in this situation. Our first equation is v is equal to gt, where v is the velocity of the dropped body at the end of t seconds. Similarly, the second equation becomes h is equal to half gt square, where h is the distance covered by the dropped body at the end of t seconds. The third equation becomes v square is equal to 2gh, where v is the velocity attained by the dropped body at the moment it covers distance h. In the second case, we consider a body projected vertically downward with some initial velocity. In this case, the initial velocity of the body is not 0. The acceleration a is again the acceleration due to gravity g. By substituting a is equal to g in the three equations, we get the revised equations as shown. Acceleration due to gravity is positive in this case, as well as the velocity of the body increases downwards. However, in the third case, the body is projected vertically upward. In such a scenario, the velocity of the body decreases as the body ascends. Therefore, the acceleration of the body becomes negative. By substituting a is equal to minus g in the three equations, we get the revised equations as shown. How much do you weigh? 60 kilograms? 80 kilograms? What we popularly refer to weight is actually mass. So, what's the difference? How can you gauge your real weight? Mass is the amount of matter contained in a body, while weight is the force with which a body is pulled towards the center of the earth. Thus, weight is the product of mass and acceleration due to gravity, that is, W is equal to mg. The value of g is approximately 10 meters per second square. Thus, if your bathroom scales show a reading of 60, your weight is 60 multiplied by 10, that is 600 Newton. Mass is a scalar quantity, hence it can never be zero. However, weight is a vector that can be zero when the acceleration due to gravity is zero, for example in space. In the SI system, mass is quantified in kilogram, while the unit of weight is Newton. A physical balance is used to measure the mass of a body. Weight is generally measured using a spring balance. The mass of a body is universal, meaning it remains the same throughout the universe. The weight of a body varies from place to place depending upon the gravitational force on the body at that place. This means that your mass on the Earth and on the Moon would be the same, but your weight would differ, because the acceleration due to gravity on the Moon is different from that on Earth. The gravitational force of the Moon is far less than that of the Earth. That's why, before cosmonauts fly on a mission to the Moon, they are acclimatized in a simulated lunar environment. This is to ensure that when they land on the Moon, they are able to move around easily even though the gravity is reduced. Because of this difference in gravity, the weight of a cosmonaut on the Moon differs from his weight on Earth. Let's find out how much this difference is. The mass of the Moon is 7.35 into 10 raised to the power 22 kilograms, and its radius is 1.74 into 10 raised to the power 6 meters. The mass of Earth is 5.97 into 10 raised to the power 24 kilograms, and its radius is 6.37 into 10 raised to the power 6 meters. Using the universal law of gravitation, we can find the force or weight of an object of mass m on Earth and the Moon. By substituting the values and solving, we get the weight of the object on the Moon as 2.43 into 10 raised to the power 10 into g into m. Similarly, we get the weight of the object on Earth as 1.47 into 10 raised to the power 11 into g into m. By comparing these results, we can determine the relationship between the weight of an object on the Earth and the Moon. Thus, the weight of an object on the Moon would be approximately 1/6 of its weight on Earth. For example, if the cosmonaut weighs 600 Newton on Earth, he would weigh approximately 100 Newton when he lands on the Moon. This brings us to the end of this lesson on the universal law of gravitation. In this lesson, you have learned about gravitational force, universal law of gravitation, free fall, and acceleration due to gravity. The following section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points, according to the law 42 of the laws of cricket, the bowling of fast short-pitched balls is dangerous and unfair if they are likely to inflict physical injury on the striker, irrespective of the protective equipment he may be wearing. How could a small object like a ball inflict injury on a cricketer? The impact of a moving object differs based on its momentum, which is the product of the body's mass and velocity. A cricket bowling technique devised in the 1930s called body line involved aiming fast-paced balls at the shoulders of the batsman. In the past, many batsmen have been injured due to the impact of balls travelling with high momentum. In this lesson, you will learn about momentum and the second law of motion. At the end of this lesson, you will be able to identify the significance of momentum, state Newton's second law of motion, derive the expression for the measurement of force, and explain the impact of change in momentum in terms of impulse. To analyze the concept of momentum, let's compare the impact of moving objects in different situations. Observe the marble dropped onto the thin glass pane below. The glass pane is intact. But what happens if we drop a cricket ball onto this glass from the same height? Ouch! The glass pane shattered. Why did the glass pane shatter this time? What was different in the two situations? The height from which the marble and the ball were dropped was the same. So was the velocity of both the objects when they struck the pane. Clearly, it must be the bigger mass of the cricket ball that made a difference. As the mass of the cricket ball is more than that of the marble, its impact on the glass pane is higher than that of the marble, and thus it shattered the glass pane. Let's now look at another case where two identical marbles, say P and Q, are dropped onto a thin glass pane from different heights. First, we drop the marble P on a thin glass pane from a height of 1 meter. The marble P does not damage the glass pane. Now we drop another marble, Q, from a greater height. Wow! Dropped from a greater height, even this small marble has shattered the glass pane. Why was the glass pane shattered by the marble Q and not by the marble P, even though the mass of both the marbles is the same? As the height from which an object is dropped increases, the velocity with which it strikes the ground or any other reference level also increases. Being dropped from a greater height, the velocity at which the marble Q strikes the glass pane is greater than that of P. Hence, the impact of marble Q on the glass pane is greater than that of P. That's the reason marble Q shattered the glass pane while marble P did not have much impact on the glass pane. Based on these observations, we can say that the impact of any object on the other depends on two factors of the object causing the impact, namely, its mass and velocity. These two factors together constitute a physical quantity, called the momentum of a moving object. The momentum of an object is the product of its mass, m, and its velocity, v. It is denoted by the small letter p. Thus, you can express momentum as P is equal to mv. Momentum is a vector quantity. It is measured in kilogram meter per second or Newton second in the SI system and in gram centimeter per second or dyne second in the CGS system. Because of its momentum, a fast-paced cricket ball can hit and hurt the batsman or the wicket-keeper if the batsman is not able to play the ball properly. That's why batsmen on the cricket field wear protective helmets and body pads to prevent possible injury. Momentum helps us understand the impact of collisions and explosions. For example, it explains the impact of a collision between two trucks or a cannon firing. The greater the momentum of an object, the larger the impact is on the other object. Remember period films where we often saw columns of armies who used huge logs to break down the gates of a fort? The group of men holding the log goes back a fair distance from the gate. Then they run to the gate to ram the log into the gate for maximum impact. The velocity and the mass of the log together provide enough momentum to break the gates down. The momentum of this army column differs at different points in their run-up to the gate. Although the mass of the log is constant, their velocity is increasing constantly. That is, they are accelerating. Another example is when actors in movies perform stunts, such as breaking down a door. the momentum of an object increases when it accelerates. Therefore, the rate of change of momentum depends on the acceleration of the object. Newton's second law of motion states that the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction of the applied force. Let's verify this law using an example. Observe this billiard table. The yellow ball is at rest right now. However, when the cue ball hits the yellow ball, it is set into motion. After being hit, the cue ball moves with less velocity while the yellow ball moves with more velocity. Thus, there is a change in velocity of both the balls, that is, a change in their momentum. Additionally, the direction of motion of the yellow ball is the same as the direction of motion of the cue ball. Now let's observe what happens when the cue hits the yellow ball with more force. As you can see, the yellow ball now moves a longer distance than the last time, before coming to rest again. Thus, when the force applied by the cue ball increases, the momentum of the ball increases as well. Hence, we can say that the rate of change in momentum of an object is proportional to the force applied on it. A lot of our actions are based on the second law of motion. Observe the cricket fielder reaching out to catch a fast-moving ball. As you can see, he pulls his hands back to catch the ball. Why does he do that? He does that to reduce the impact of the fast-moving ball on his hands, before bringing its velocity down to zero. By pulling his hand back, he increases the duration of time taken in bringing the velocity of the ball to zero. Newton's second law of motion can be expressed mathematically as F is equal to ma, where F is the force applied on a body, measured in Newton in the SI system and in dyne in the CGS system. M is the mass of the body, and A is the acceleration produced in the body. Let's derive this relationship using an example. Consider a ball of mass m having an initial velocity u. When a force of magnitude F is applied on the ball for time t, the ball moves ahead with an acceleration a. In the time period t, the ball accelerates to a final velocity v. Let P1 be the initial momentum and P2 be the final momentum of the ball. By the definition of momentum, P1 is equal to mu. P2 is equal to mv. Hence, the change in momentum is P2 minus P1 is equal to mv minus mu, or m multiplied by v minus u. The rate of change of momentum is the ratio of change in momentum to time. That is, m multiplied by v minus u divided by t. According to Newton's second law of motion, the rate of change of momentum is proportional to the force applied. This gives us the relationship F is proportional to m v minus u divided by t. The acceleration a of the ball is the ratio of change of velocity v minus u to time t. Hence, we can write this relationship as F is proportional to ma. We use a constant of proportionality k to equate this relationship. Therefore, F is equal to kma. In the SI system, a unit force is a force with a magnitude of 1 Newton. Unit force is defined as a force that produces unit acceleration, that is, 1 meter per second square, when applied on a body of unit mass 1 kilogram. Thus, substituting the values in the expression, F is equal to kma, and simplifying, we get the value of k as 1. Hence, we get the mathematical expression of the second law of motion as F is equal to ma. Therefore, according to second law of motion, you can express the force applied as the product of mass and acceleration of the body. Using the expression for second law of motion, we can define the relationship between the SI unit of force, Newton, and the CGS unit, dyne. Consider unit values for force, mass, and acceleration of an object, and substitute these values in expression F is equal to ma. You get 1 Newton is equal to 1 kilogram meter per second square. Since 1 kilogram equals 1000 gram and 1 meter equals 100 centimeter, 1 Newton is equal to 10 raised to the power 5 gram centimeter per second square. Since 1 dyne is equal to 1 gram centimeter per second square, 1 Newton is equal to 10 raised to the power 5 dyne. Let's again look at the second law of motion. According to this law, force equals rate of change in momentum. Rearranging the expression, change in momentum equals product of force and time. When a large amount of force acts on an object in a very short duration of time, it is termed as impulse. Here is an example of a situation where we see impulse at work. Consider a cricket ball bowled towards a batsman in a cricket field. The batsman strikes the ball with a large force that acts on the ball for a moment. The impact of the bat enables the ball to change its velocity in magnitude as well as direction. This is the impulse of the bat on the ball. Impulse is numerically equal to the change in momentum. Impulse is denoted by J and is measured as a product of force and time. As the impulse of a body is numerically equal to change in its momentum, the unit of impulse can also be expressed by the unit of momentum. Thus, the SI and CGS unit of impulse are Newton second and dyne second respectively. In karate, a man can break a brick with his bare hands, even though the mass of his hand is small. The high acceleration of the strike provides enough force of high magnitude to his hand to break the bricks. This large force acts on the brick for a short duration, making an impulse. This impulse helps to break the bricks. This brings us to the end of this lesson on momentum and the second law of motion. Hope this session provided you with an understanding of the concept of momentum and Newton's second law of motion. Now you can use the mathematical expression for force to solve problems in physics. The section Unsolved Problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. Remember the hare and tortoise story your granny read to you in your childhood? The story goes like this. A hare was watching the slow progress of a tortoise on a path in the jungle. Being a faster runner himself, he began to make fun of the tortoise. The tortoise challenged the hare to a race, and the hare accepted confidently. When the race began, the hare shot ahead and ran briskly for some time. Then, seeing that he was far ahead of the tortoise, he decided to sit and relax for a while before continuing the race. He soon fell asleep. The tortoise, plodding on, overtook him and finally won the race. The table provided shows the data on their progress during the race. Similarly, the graph represents the same data. Can you see how the hare was making progress? But the hare lagged behind in the end because he stopped at 1.8 kilometers. The tortoise, on the other hand, walked without stopping and made steady progress. Isn't it easy to make out who won the race and how? Graphs help us communicate information visually. They enable us to understand quickly trends that would otherwise need lengthy written descriptions. As you have studied in mathematics, a straight line graph helps in solving a linear equation with two variables. In this lesson, you will learn about graphical representation of motion. At the end of this lesson, you will be able to explain how graphs can be used to represent and solve problems related to motion, plot various types of distance-time graphs, calculate the speed of an object at a given instant using the distance-time graph, plot various types of velocity-time graphs, calculate displacement using a velocity-time graph, identify the significance of equations of motion, derive the equations of motion, and explain the concept of uniform circular motion. Graphs typically contain both an independent and a dependent variable. For example, consider the graph shown. It plots the runs scored by a cricket team in a one-day match. If you observe the cricket match graph, the number of overs bowled in a match is independent of how many runs came off an over or how many wickets were taken. Since the number of overs is an independent quantity, it is taken on x-axis. Similarly, we can use line graphs to describe the motion of an object. In motion graphs too, physical quantities such as distance or velocity show dependence on time, while time is an independent quantity. Therefore, time is always taken on the x-axis and the other physical quantities are taken along the y-axis. You can create graphs in motion by comparing distance, displacement, or velocity to time. By representing the motion of an object graphically, you can infer the nature of motion, determine its position at any interval, calculate its acceleration, displacement, velocity, etc. at any instant, and derive equations of motion. Two of the most commonly used motion graphs are the distance-time graph and the velocity-time graph. A distance-time graph represents the change in the position of an object with time. In such a graph, time is taken along the x-axis and distance is taken along the y-axis. The graph is plotted adopting a convenient scale for the distance and time. For example, you can use a scale of 1:10 on the x-axis for time. A scale of 1:10 means that each unit on the graph represents 10 seconds. Let's see how a distance-time graph is plotted using some sample data. To plot the distance-time graph, we begin with fixing two axes, x and y, on a sheet of graph paper. On the x-axis, we mark the equal time intervals according to a convenient scale. Say 1 unit equals 10 seconds. Again, using a convenient scale on the y-axis, we mark the y-axis at equal intervals. For example, as mentioned earlier, your scale could be 1 unit equals 10 meters. For each set of figures, locate and plot a point at which the perpendiculars drawn from the respective time and distance values on the axis intersect. Finally, we connect all the points, starting from the origin using straight lines. This gives us a distance-time graph for the data provided. Considering the nature of the motion of a body, a distance-time graph may show a body at rest, a body with uniform motion, and a body with non-uniform motion. If a body is at rest and does not move, we say the distance travelled by the body is zero, no matter how much time has elapsed. The distance time graph for such a body at rest is plotted as a straight line along the x-axis. However, consider a situation where the body has already travelled a distance of 5 meters. When we start analysing data on its movement, it means that the body is at 5 meters at 0 seconds. If the body continues to be at the same position for the rest of the time, then the graph is a straight line parallel to the x-axis. When a body exhibits uniform motion, it travels equal distances in equal intervals of time. For example, consider a body moving with uniform speed. The data provided represents the position of the body at different instances of time. The initial position of the body is 0. The graph for this body is a straight line, making an angle with the x-axis and passing through the origin. Thus, the graph of a body in uniform motion is an inclined straight line passing through the origin. When a body exhibits non-uniform motion, it travels either unequal distances in equal intervals of time or equal distances in unequal intervals of time. For example, the table gives the position of a body at different instances of time. When we plot the distance time graph for the data given, we observe that the distance time graph for a body having non-uniform motion is a curve. Let's analyze this data further. During the first 10 seconds, the distance travelled by the body is 5 meters. Thus, the speed of the body for the first 10 seconds is 0.5 meter per second. For the next 10 seconds, the distance covered by the body is 10 meters. Hence, the speed of the body during the second 10-second interval is 1 meter per second. We observe that the speed of the body increased with time at a constant rate. Hence, we can say that the body moves with uniform acceleration. Thus, for a body with uniformly accelerated motion, the distance time graph is in shape of a parabola. Now let us consider a body moving unequal distances in equal time intervals. As you can see, a graph plotted based on the data provided again shows a curve. Now, let's look at how we can use the distance time graph to make deductions about speed. To determine the speed of an object, consider a segment PQ of the distance time graph of an object in uniform motion. Draw a line parallel to the y-axis from point Q and another line parallel to the x-axis from point P. These parallel lines intersect each other at point R to form a triangle PQR. On the graph, PR denotes the time interval, while QR corresponds to the distance. You can see from the graph that as the object moves in time interval t2 minus t1, the distance it covers is s2 minus s1. By definition, speed is the ratio of distance covered to the time taken in covering that distance. Therefore, the speed of an object v is equal to s2 minus s1 divided by t2 minus t1. Note, you can also use the term uniform velocity in place of uniform speed if the magnitude of displacement equals the distance travelled by the object along the y-axis. Like the distance-time graph, the variation in velocity with time for an object moving in a straight line can be represented by a velocity-time graph. In a velocity-time graph, time is taken on the x-axis while velocity is taken along the y-axis. Using a velocity-time graph, you can determine the nature of the motion, the velocity of the body at any instant, displacement of the body as the area under the graph, the instantaneous acceleration, and the equations of motion along a straight line. Let's consider the different cases that can be represented by a velocity-time graph. Body at rest. Body with uniform velocity. Body with uniform acceleration. Body with non-uniform acceleration. And body with uniform retardation. The displacement is 0 for a body at rest, and hence the velocity is also 0. A velocity-time graph plotted for a body at rest displays a straight line along the x-axis. When a body moves with uniform velocity, there is no change in the velocity with respect to time. Therefore, the velocity-time graph for a body with uniform velocity will be a straight line parallel to the x-axis. The point where the line intercepts the y-axis shows the magnitude of the uniform velocity of the body. When a body exhibits uniformly accelerated motion, the velocity-time graph represents a straight line passing through the origin and subtending an angle with the x-axis. This is because in this motion, the velocity of the body increases uniformly with time. The velocity-time graph for a body moving with non-uniform acceleration is a curve and not a straight line. The velocity-time graph for a body moving with uniform retardation is a straight line making an obtuse angle with the x-axis. Just as you can use a distance-time graph to determine the speed of an object, you can use a velocity-time graph to determine the displacement of an object. The area under a velocity-time graph gives you the displacement of the body in a given time. Consider the velocity-time graph of a car moving with uniform velocity, say 30 meters per second. To determine the displacement of the car between points A and B, which represent the position of the car at durations 20 seconds and 30 seconds respectively, draw perpendicular lines from A and B to intersect the x-axis at point C and D respectively. The time taken, t, by the car to move from the position represented by point A to the position represented by the point B is the difference of time t2 and t1. We can say AB is equal to CD is equal to t2 minus t1 is equal to 30 minus 20 is equal to 10 seconds. Since the car is moving with a uniform velocity, the magnitude of its velocity is the same at all points on the graph. Velocity v is equal to AC is equal to BD is equal to 30 meters per second. By definition, the velocity of an object is the ratio of displacement to time. Therefore, we can say that displacement is the product of velocity and time taken. Substituting v and t in the expression S is equal to Vt, we get S is equal to AC multiplied by AB. This is nothing but the area enclosed in rectangle ABCD under the velocity time graph. Thus, in this case, the displacement of the car is equal to 30 meters per second multiplied by 10 seconds is equal to 300 meters. Similarly, you can also determine the displacement of a body moving with uniform acceleration. Consider the velocity time graph. To determine the displacement of the body between points A and E, from both points A and E, draw two lines parallel to the y-axis, intersecting the x-axis at points B and C respectively. From point A, draw a line parallel to the x-axis to intersect the line CE at D. The area under the velocity time graph between points A and E is the sum of the areas of the rectangle ABCD and the triangle ADE. Hence, the displacement is equal to S is equal to AB multiplied by BC plus half of AD multiplied by DE. Analyzing a velocity time graph enables you to derive the equations that define the relationship between velocity and acceleration of a body moving in a straight line. These equations are collectively referred to as equations of motion. There are three equations of motion. V is equal to U plus AT. S is equal to UT plus half AT square. 2AS is equal to V square minus U square. These equations are used to determine the position, velocity, and acceleration of an object. We can derive these equations graphically. The first equation of motion is known as the velocity-time relation. Consider a velocity-time graph for a uniformly accelerated moving object as shown. In the graph, u is the initial velocity of the object represented by the point A. V is the final velocity represented by the point B. T is the time in which velocity changes from u to v. From point B, draw two lines BC and BE perpendicular to the x-axis and the y-axis respectively. From point A, draw a line AD parallel to the x-axis to intersect BC at D. Now, OA represents the initial velocity u. BC represents the final velocity v. OC represents the time t. And BD represents the change in velocity in time t. OADC being a rectangle, OC is equal to AD. And hence, AD also represents the time t. BC is equal to BD plus DC, which is equal to BD plus OA. Let's call this equation 1. Substituting BC is equal to V and OA is equal to U in equation 1, we get V is equal to BD plus U, or BD is equal to V minus U as equation 2. The acceleration of the object is the ratio of change in velocity to time taken. From the graph, acceleration A is equal to BD divided by AD, which is equal to BD divided by OC. Let's call this equation 3. Substituting OC is equal to T in equation 3, we get A is equal to BD divided by T, or BD is equal to AT as equation 4. Equating equations 2 and 4, we get AT is equal to V minus U. Therefore, V is equal to U plus AT. Let's now derive the second equation of motion, that is position-time relation. In the same velocity-time graph, we used to analyze position-time relation. Let S be the displacement of the object in time t. You can determine the displacement of the object as the area of the trapezium OABC under the curve. The area of OABC is the sum of the areas of rectangle OADC and triangle ABD. Area of a rectangle is product of its length and breadth, while the area of a triangle is half the product of its base and height. Area of OABC is equal to OA multiplied by AD plus half of AD multiplied by BD. Substituting OA is equal to U, AD is equal to OC is equal to T, and BD is equal to AT, which equals S is equal to U multiplied by T plus half of T multiplied by AT. Therefore, S is equal to UT plus half AT square. The third equation of motion, called position-velocity relation, is derived using the first two equations. In the velocity-time graph, the displacement of the object S is also equal to the area of trapezium OABC. Area of trapezium OABC is equal to half of OA plus BC multiplied by OC. Substituting OA is equal to U, BC is equal to V, and OC is equal to T, we get S is equal to half of U plus V multiplied by T as equation 1. Rearranging the velocity-time relation, we get T is equal to V minus U divided by A. Let's call this equation 2. Substituting equation 2 in 1, we get S is equal to V plus U multiplied by V minus U whole divided by 2A. By simplifying this expression, we get the position-velocity relation. That is, 2AS is equal to V square minus U square. Consider the movement of the seconds hand in a clock. As the clock ticks, the tip of the hand moves in a circular path, covering equal distances in equal time intervals. In each time interval, the hand subtends the same angle at the center of the clock. Such a motion, when an object moves in a circular path with uniform speed, subtending equal angles at the center of the circle in equal intervals, is called uniform circular motion. Other examples that you can relate to include the rotation of the Moon and the Earth, a satellite in a circular orbit around the Earth, and so on. How would you calculate the velocity or the distance covered during uniform circular motion? Let's analyze the example of an athlete who is running along a circular track. The distance covered by the athlete at the end of one lap is equal to the circumference of the track. S is equal to 2 pi r. The speed of an object is the ratio of displacement to time. Hence, the speed of an object in uniform circular motion is v is equal to 2 pi r divided by t, where r is the radius of the circular track and t is the time taken to circumnavigate the track once. Thus, you can use this formula to determine the speed of an object in a uniform circular motion. This brings us to the end of this lesson on graphical representation of motion. In this lesson, you learned how to use graphs to analyze trends and derive and apply equations of motion. You also learned about uniform circular motion. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.
Way to go, Bumbo! You need to use more force to get your cap back.
You used the word force. But do you know what the word force really means?
Well,
the word force is used in a variety of situations in common parlance. However, in science, force is what acts on a body to make it move or stop it from moving. In this lesson, you will learn about force, its effects, and its characteristics. At the end of this lesson, you will be able to define force, illustrate the effects of force, list the characteristics of force, distinguish between balanced and unbalanced forces, and explain friction. To explain the concept of force, let's first observe some real-life situations. What do you think these people are trying to do?
they're trying to perform some tasks requiring force.
That's right. As you can see, the first task involves force in kicking a ball and setting it in motion. The second requires force to roll a boulder off the cliff. In the third, force is being applied to try and stop a moving bus. Thus, if we use these examples to define force, force is an agent that tries successfully or unsuccessfully to move a body which is at rest or to stop a moving body. Let's go back to Bumbo and Jumbo and their clown act in the circus. Bumbo applies force on Jumbo, trying to push him away so that he can retrieve his cap. Initially, Bumbo does not succeed, even though he's trying hard and exerting force.
I guess he needs to push harder.
That's right. When Bumbo increases the force exerted on Jumbo, he is able to push Jumbo away.
There you go. He got his cap.
This child is applying force, trying to stop the dog from breaking free of the leash. If you have ever taken a dog for a walk, you have probably had a similar experience. A dog that is eager to get away can apply a considerable amount of force on the leash. You can say that a force is being exerted on the bodies in both these cases.
Oh. So here two forces are combined. Looks like force affects our life in a lot of ways.
True, although you can't see, taste or touch force. We all feel the effects of force. A force acting on a body can change its state of rest or of motion, its direction of motion, or its shape. Let's look at each aspect of change induced by force, one by one. In our initial example, the force applied by Bumble made Jumbo move. Similarly, a push to a stationary shopping cart sets it in motion. A child uses force to pull a box of toys on the floor. A football goalkeeper applies force on a fast-rolling ball to stop it and save a goal. In all these cases, the state of rest or of motion of an object is changed. On a hockey field, when the ball is passed from one player to another towards the goal, players use their hockey sticks to guide the ball. Do you notice that as the ball is guided with a hockey stick, it often changes its direction of motion? This change in direction is also a result of the force applied on the ball through the stick.
And how does force affect the shape of an object?
You may have noticed how a balloon man creates figures from balloons.
Yes. They do that by squeezing the balloons in different places on the balloon.
Right. By squeezing, they are applying force on the balloon. This makes the balloon expand in other areas. You can also observe this effect in a rubber band, a kitchen sponge, or a beanbag chair. A rubber band expands on pulling, while a sponge contracts on squeezing. Beanbags are popular because they take different shapes depending on the position of the person sitting on them.
So how do we identify force?
You identify force using its four characteristics: magnitude, line of action, nature, and point of application. Magnitude is the measure or quantity of a force. Magnitude of force is quantified in Newton in the SI system and in dyne in the CGS system. Look at Bumbo trying to push the two wooden blocks of different sizes towards the wall. He had no problems pushing the smaller block, but he seems to be struggling with the larger block. There, he's done it. What do you think was the difference in these two cases?
He had to apply more force to move the second block.
Correct. The magnitude of the force required to move each of the two blocks was different. The magnitude of force is indicated by the numerical value depicting the quantity of force applied and the unit of the force. Line of action is a line along which the force acts. Consider a book kept on a table. Do you think it exerts any force on the surface of the table? Doesn't look like it, does it? In fact, its weight acts as a force downwards on the table. You can say that the line of action of force is downwards. However, if you try to push the book, you need to apply force horizontally. Therefore, the line of action of the force applied on the book will be horizontal.
So, the line of action can be horizontal or vertical.
Not just horizontal or vertical. Line of action can also be inclined. For example, when a golfer hits a ball, he applies force at an angle from a horizontal surface. Hence, the line of action in this case is inclined. A force can be a push or pull force by nature. For example, a cue pushes the billiard balls forward, while a truck pulls a trailer behind it. Finally, let's look at the point of application of a force. The effect of force on a body depends on the point at which the force is applied. To understand what this means, consider the scenario where a clown in a circus is pushing another clown. when the clown is given a push on his upper body?
Oops! He fell face down.
Now, what if the point of applying the push is changed? A push on the middle of his body, for instance. Did you notice the clown didn't fall at all? He simply moved ahead. Now let's see what happens when the push is directed towards his lower body. The clown loses balance again, and this time he falls on his back. So, based on the characteristics of force, can you determine whether it is a scalar or a vector quantity?
Let's see. A force requires a magnitude as well as a direction, right? This makes force a vector.
Very good. Let's move on to learn more about types of forces.
Wow! They all seem to be applying a lot of force, but nothing is happening. How do you explain that?
So far, you have seen effects of single forces in terms of pulling and pushing. But in real life, there are often multiple forces acting on a body simultaneously. For example, in this case, there are an equal number of people on both sides. So, the force applied on one side of the rope is being counteracted by the force applied by the other side of the rope. That is, the force on both sides is balanced.
Does that mean there will be no movement if forces are balanced?
That's right. In such cases, because force is a vector, we must consider the result of the multiple forces acting on the body. This resultant force is called the net force. Net force is the sum of all the forces acting on the body. The magnitude and direction of the net force on the body depends on the magnitudes of the individual forces and their directions. If two forces, Fa and Fb, act in the same direction on a body, then the net force, Fa plus Fb, acts in that direction. In the same setup, if Fa acts in the direction opposite to Fb, and Fb is greater than Fa, then the net force becomes Fb minus Fa, and acts in the direction of force with a greater magnitude, that is, Fb. In case of multiple forces acting on a body, when the net force is zero, the forces are known as balanced forces. For example, this game of tug-of-war.
Doesn't look like this game is going to end. Neither of the teams seem to be making any progress.
Yes, this game will have to be a draw, unless we do something to tip the balance of the force. Let's see what happens if we add a person on one of the teams. See, the team with more people won. That's because adding another person made the forces on both sides unequal, and the net force was no longer zero. In such a case, the forces are said to be unbalanced. The concept of balanced and unbalanced forces applies to objects at rest as well as moving objects. When forces are balanced, a stationary object remains at rest and a moving object continues to move at the same speed and in the same direction. When forces are unbalanced, the object may change its state from rest to motion or vice versa, or change its speed or direction of motion in the direction of the net force. Let's observe this game of cricket. As you can see, the ball, when hit by the batsman, slows down and stops after rolling a certain distance. Do you see any force being applied to stop the ball?
No, ideally the ball shouldn't stop, right? No one applied any force to stop it.
The ball stopped due to a force called friction. Friction is the force resisting the relative motion of two bodies that acts along the surfaces it contacts. The bat hits the ball with a certain force that makes the ball move ahead. When the ball rolls down the field, friction acts in the direction opposite to the direction of the motion of the ball. Gradually, the frictional force overcomes the force that made the ball move, slowing down and eventually stopping the ball.
Is friction the same on all surfaces?
That's a good question. Look at this.
It needed a lot of force to push the block in the first case.
And yet, in both the cases, it is the same block.
So was it the type of surface that made the difference?
Yes. Rough surfaces offer more friction, while smooth surfaces offer minimal friction. That's why, when you try pushing a wooden block kept on a rough surface, you need to apply a relatively large amount of force to move it. Conversely, if you push the same block on a slab of ice, it moves relatively fast. You find friction at work almost everywhere around you. Some examples are objects lying on a slightly inclined plane, pens, pencils, and chalk in use, automotive brakes, and force between vehicle tires and the road when in motion. This brings us to the end of this lesson on force. In this lesson, you have learned about effects of force, characteristics of force, balanced and unbalanced forces, and friction. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson.